All right, chapter 3, section 4. We're going to be talking about cells. So you go to topics, chapter 3, cells. You hit the chapter 3 notes here. It's going to pop you into copy of 3.4, and we are off talking about passive transport. Passive transport does not require energy from the cell. And when you think of energy, I want you to think of energy currency, which is ATP. ATP, which is Alpha Tango Papa. Right? That's just a 3-letter acronym for the energy currency of the cell. You don't need any, so this happens automatically. And we're going to give you some examples of this sort of transport. Transport, again, is moving stuff. I don't know if that was painfully obvious to you. So we're moving stuff, and it doesn't require energy, which is always a great thing. There's 2 types of passive transport: diffusion and osmosis. Not Osmosis Jones. It's just a name. So osmosis is a process, which is where that name came from, and we'll go from there. So you might have done this where you added food coloring to water and you wait a little bit and it almost mixes all by itself. If you just kind of leave it there, it just kind of mixes and stuff. Or when you make the great and fabulous Kool-Aid like we did in chapter 2, you actually had diffusion occur, where you just pour it in and it automatically mixes on its own. That is an example of passive transport. Okay? Why? Because it happened by itself. I didn't have to do anything for it to happen. It just happened. That's passive transport. So what happens is molecules travel down a concentration gradient. You're like, oh goodness, what is that? Well, look at this pile of dark green, almost black. Here, right? Here there's a lot of food dye, which is what's in this bottle. And then here in the water, there's none. So there's a bunch here and none here. It's a high concentration and a low concentration here. This is called a concentration gradient because you have a bunch in one spot and a little bit in the other. And traveling down, it goes from high to low. Now remember, it doesn't mean like altitude high to low. It means from where there's many to where there's few. And sometimes it's actually going many to few. And it'll go up, like upwards, but it's still moving down the concentration gradient. I just don't want you to get stuck with the idea that it always has to move downward. Sometimes we cannot move the dye, right? The dye can't move. An example of this would be like, well, here. When you have Chinese food, or if you have a lot of Domino's pizza, sometimes you get really, really thirsty, right? Because what's happening is you consume a lot of salt, monosodium glutamate, MSG, I think it's how you say it, is a salt. It's a preservative salt. And what ends up happening is it does not go into our cell membranes, at least not that I know of. If it does, that's probably bad. But it makes you very, very thirsty. So what ends up happening is you'll be sitting there, you'll eat a bunch of Chinese food, you will get a lot of MSG in your body, and you'll become very, very thirsty. Because since the solute, right, not the food dye, but the MSG, can't travel across the membrane, water does. So when diffusion can't happen, water diffuses in a process called osmosis. So let me give you an example. So here's your normal water amount, okay? Your normal cell. Here's a cell, there's a good amount of water coming in, a good amount of water coming out. You eat a bunch of salt. And now there's a bunch of MSG out here. A bunch of MSG out here. So what your body does is it sends you a message. You're thirsty. And then your brain's like, hey, I'm thirsty. So then you will drink water, hopefully, right? To try to balance this back here. So this is called isotonic, where the amount of water that goes in and the amount of water that goes out is in balance and is in a good place. Hypertonic means there's extra solute on the outside and the cell is shriveling because that solute can't transverse the cell membrane. It's kind of stuck on one side. So the water floods outside to try to dilute the salt, the MSG. Now, maybe you drink a gallon of water. Let's just say, okay, so you're here, you had Chinese food, now you're all, your cells are shriveling up and they're shooting water out to try to balance the MSG concentration in and out, and they can't do it. It's almost impossible. So you drink a gallon of water. Well, now you have way too much water because you flushed out all the MSG, and now water's rushing into your cell. So what does your cell do? Your body do? It starts to take that water out through your kidneys, and you have to go to the bathroom. You have to urinate. So, and you'll keep doing that until you get back to isotonic. So isotonic is when it's even. Iso means even. Hyper means extra, right? So the solution is hypertonic, right? Hypotonic, right? The solution has too much water. This has too much salt, not enough water. This has too much water. It's the opposite for the cell. So if the solution is hypertonic, the cell is hypotonic. And if the solution is hypotonic, the cell is hypertonic. And the water always goes to the hyper, right? Water always flows to where it's hyper. And you can tell where the water's going based on which one's filling up. Is the area outside filling up, or is the cell filling up? Sometimes things can get through a membrane, but they need to get through a membrane using a protein, a protein channel. For us, it's like, we can't really get through walls. Like when we go into a classroom, we can't get through the walls. We have to go through a door, right? For the most part, some of you, maybe go through walls or windows or something. But for the most part, us humans, we go through doors. So in that sense, some molecules cannot go across the membranes unless they go through doors. And maybe they're the wrong size, maybe they have the wrong charge, maybe they're polar when they need to be non-polar, etc. Whatever it is for that particular thing, it can't get through unless it goes through the protein channel. That's facilitated diffusion. It's diffusion because there's no energy needed, and it's facilitated because it's made easier by the protein. By the way, this movement of water is all types of osmosis. They're all examples of stages of osmosis, and none of them use any energy at all. This is all automatic, no energy needed. It happens without you wanting it to happen. And that's it for chapter